Hello again, everybody, and welcome to yet another contemporary math video, this time over section 9b, and we are going to continue looking at linear modeling in this video. So we have a rate of change rule to start us out. The rate of change rule is change in the dependent variable will equal the rate of change times the change in the independent variable. So we can jump right into some examples, and we want to write a statement that describes how one variable varies with respect to the other. Give the rate of change numerically with units. Use the rate of change to answer any questions. Example 1. Every week, your fingernails grow 5 millimeters. How much will your fingernails grow in 2.5 weeks? 2.5 weeks. So we want to write a statement that describes how one variable varies with respect to the other. So the statement will look something like this. The dependent variable varies with respect to the independent variable, comma, with a rate of change of the rate of change that's given. So for our first example, we can answer like this. The length of your fingernails varies with respect to time with the rate of change of 5 millimeters per week. So the length of your fingernails depends on your time. So the length of your fingernails is the dependent variable, and time is your independent variable. And we knew it was going to be time because if you look at the words that are used here, week and millimeters, we know that this describes the length of the fingernails and that this describes the time. From there, we know that it will be 5 millimeters per week. So we can always use the number for the rate that we're given here, 5, and we will have the dependent units, millimeters, right? Length of your fingernails was in millimeters, divided by the independent units, y's over x's, rise over run. So from there, we can use the rate of change rule to answer the question, how much will your fingernails grow in 2.5 weeks? This is an independent value, a change in your independent variable. And we just have to multiply that by the rate of change, and we will figure out how long the fingernails will grow in 2.5 weeks. Pretty simple. So even the units work out here. Let's take our rate of change, 5 millimeters per week, and we multiply it by 2.5 weeks. The units here for the weeks will indeed cancel each other out. So they will cancel. And we are left with 5 millimeters times 2.5, which would be 12.5 millimeters. For the second example, the water depth in a lake decreases at a rate of 2 inches per day because of evaporation. How much does the water depth change in 8 days? Or in 15 days? Our statement here would be, the water depth varies with respect to time at a rate of -2 inches per day. And you might be wondering, why did I throw this negative in here? And that is because this word right here decreases. So if it decreases, we know that the rate will be negative. So then we just have to go on and figure out. We know that it has to be the rate times the change in the independent variable So I want to point out again here that the water depth is the dependent variable, and time here again is the independent variable. So if we multiply the rate times the change in the independent variable, again, the days here will cancel, leaving us with negative 16 inches, which means the depth of the water will decrease by 16 inches. And we can do something very similar for the 15-day period. If we have negative 2 inches per day times 15 days, then we get negative 30 inches, which is pretty drastic, I think. That's a drop of 2.5 feet. All right, example 3. A 1 degree change, increase or decrease, on the Celsius temperature scale is equivalent to 9/5 degree change on the Fahrenheit temperature scale. How much does the Fahrenheit temperature increase if the Celsius temperature increases by 11 degrees? And then we have a similar question by how much does the Fahrenheit temperature decrease if the Celsius temperature decreases by 23 degrees? All right. So the sentence for this is, I think we should figure out first what the independent and dependent variables are. It seems as though the Fahrenheit temperature would be the dependent variable, because we're talking about how the Celsius temperature changes and how that affects the Fahrenheit. The Fahrenheit here depends on how much the Celsius temperature changes. So this will be dependent, and the Celsius temperature will be the independent variable here. So you can try writing your sentence, and I will come back in a few seconds with the sentence I found. The Fahrenheit temperature varies with respect to the Celsius temperature at a rate of change of 9/5 degree Fahrenheit per 1 degree Celsius. So how would we use this rate to find the Fahrenheit temperature increase compared to a Celsius temperature increase of 11 degrees? Well, we multiply the independent variable value of 11 degrees by the rate. Now, if you do this straight across, like you've learned how to multiply fractions, you end up with a 99/5 degree Fahrenheit change. But most people would understand this better if it were a 19.8 degree Fahrenheit change. And in fact, this all would be positive because of the increase of 11 degrees. Now, if there was a decrease, like this second example, it decreases by 23 degrees, we would have to say 9/5 times a negative 23. And again, we could put that over 1. And this would give you a negative 207/5 degree Fahrenheit drop, right? The negative tells you it would decrease, but again, it would make more sense as a 41.4 degree drop. On this page, we'll take a look at the general equation for a linear function. So you may see here that we have this equation written out in words. We have the dependent variable equals the initial value plus the rate of change times the independent variable. And that should feel pretty normal, as we were multiplying the rate of change by the independent variable on the last slide. So we can relate this back to an equation we've seen already, y equals mx plus b, where this is the rate of change, the slope as we've been calling it. And you'll notice that the rate of change is being multiplied by the independent variable, which we've always called x. The dependent variable y is already isolated on the left. And that means this b, this plus b, was what we would call the initial value. But in the context of this equation, we also called it the y-intercept. And the y-intercept would have coordinates at 0, b, whatever this number is. The last thing here to talk about is the initial value, and that is the value at time equal to 0. So, and usually, well, I think in these examples that we're going to be looking at here, the independent variable will be time. So this just matches up with exactly what we were talking about. When the independent value is 0, that gives us our initial value. All right, so in the following examples, the situations can be modeled by linear functions. In each case, we want to write an equation for the linear function and use it to answer the given equation. Be sure you clearly identify the independent and dependent variables. Then briefly discuss whether a linear model is reasonable for the situation described. So here's a spoiler alert for everyone out there. Briefly discuss whether a linear model is reasonable for the situation described. When we look at examples 4 through 7 down there, a linear model will be reasonable. The way you can tell is that there won't be any increasing or decreasing by a given percent. Remember, if you're increasing or decreasing by the same percent each time period, then it would be modeled by an exponential function. So this statement here, yes, a linear model is reasonable for everything we're going to look at on this slide. All right, let's take a look then at the first example, example 4. A collectible baseball card is worth $120 this year and might gain about $30 in value each year. What could the value of the card be in 5 years? So the first thing we want to do is we want to come up with some variables. The most common variables that we use are x and y, like we used up here. But in the real world, you may want to pick variables, letters, that are more what I would say descriptive of the variables you're working with in words. So, right, we have the collectible baseball card is worth $120. Why don't we use worth to be the worth, or W to be the worth of the baseball card? And why don't we let T be our time? And again, we would use units here. This would be dollars, and this would be years. So now we can set up an equation. So the worth would be, what do we want? The initial value. That would be $120. That's how much it's worth right now. And we think it would grow $30 each year. So $30 each year. And we can now estimate the value of the card 5 years later. So the worth would be $120 originally plus $30 it would grow each year for 5 years. 30 times 5 is 150. 150 plus 120 is $270. Let's take a look at example 5. So in example 5, we have in 2012, Dana Vollmer set the women's world record in 100-meter butterfly with a time of 55.98 seconds. So you'll notice the unit here for time is seconds this time. Assume that the record falls at a constant rate of 0.05 seconds per year. What does the model predict for the record in 2020, the year I'm making this video? Let's see how this will work. So what do we want? We want our variables. How about we use R for record, world record time, and T for time. This time, the world record units would be in seconds, but the time would still be in years. So now we can set up this equation. The dependent variable would be equal to the initial value of the world record, which is 55.98, and we will subtract this time because the world record falls at a constant rate. So if we're falling, that means we will be taking it away. So we will subtract 0.05 t. From here, we can multiply the independent variable by the rate, 0.05 times 8. So when you multiply these two values together, you get 0.4. So this would equal 55.98 minus 0.4, which would equal 55.58 seconds. And you may be wondering, why did I use 8 for time? Well, at the very beginning of this problem, when this problem is set, in 2012 is when she set this record. So in 2012, between 2012 and 2020, there are 8 years that pass. So I would use 8 for the number of years. Okay, I'm going to give you a chance to try a couple for yourself. Here's number 6 and number 7. So try these for yourself. Define your variables, come up with an equation, and then answer some questions here. 6b might be a bit of a challenge, but see if you can figure it out anyway. All right, for number 6, the cost of leasing a car is $1,000 for a down payment and $360 per month. So we can call the cost C in dollars and the time T in months. So the equation would then be the cost is the initial amount, aka the down payment, $1,000, plus $360 for each month you lease the car. Now, part A is asking, how much will you have paid in 5 months? So we know this is a time that we're given, and we can substitute 5 in for the t, just like this right here. We can multiply 360 times 5 and get 1,800. From there, we can add 1,000 and 1,800 to get 2,800, and I should be a little more specific about this. These are $2,800. Next, we have a question for how many months. So that already right there is telling us we don't know how much time. Can you lease a car with $3,680? So this is the total cost that you have available to you. This is the maximum cost you can afford. So we put this value in for C and we get this particular equation. Now we're back to solving equations. So we need to subtract 1,000 and we can get 2,680 equals 360t. And to solve for this, we can divide by 360 to get the opposite. And these will cancel out to 1, remember, these cancel out to 0. We will get that t equals 7, but we have to include the unit months. All right, as far as the kitten is concerned, the kitten weighed 2 pounds at birth and 10 pounds 1 year later. So between these two numbers, there's a hidden rate. If you take the difference of these numbers, 10 minus 2, you can see that the rate would be 8 pounds per year. So the dependent variable would be the current weight, which I am calling W, and the time here is in years, and we will represent that by T. So the weight is 2 pounds at the beginning plus 8 pounds for each year after that. So after 3 years, your kitten would weigh 2 plus 8 times 3, which is 26 pounds. After 8 years, your cat would weigh a whopping 66 pounds. So this is concerning. This is the weight of a 10-year-old child. No cat should be weighing that much. So we have to put a little asterisk here. This is only accurate for young ages. And the same thing works for multiple scenarios. You can break linear models very easily. So say a child is born weighing, let's say 8 pounds, and they gain 15 pounds each year. Well, if you live to be 50 years old, now you're going to weigh roughly 800 pounds, and that's too much. You can also break linear functions, like if you have a bar of soap and it weighs 200 grams and you use 10 grams each day. Well, how much soap will you have left after 30 days, after a month? You would end up with negative 100 grams of soap. And so linear models do a pretty good job of modeling real world information, but sometimes it can only do it in a very limited scope. The last slide here, we're going to take a look at graphing linear functions. And so here for these examples, we have the following situations can be modeled by linear functions. In each case, draw a graph of the function and use it to answer the question. Be sure to clearly identify your independent and dependent variables, and then same thing here with this statement. Briefly discuss whether the linear model is reasonable. Guess what? We're talking about linear equations, so a linear model will be reasonable for these. Again, you won't see any increases of by percentages. You'll just see flat increases. All right, let's look at example 8. We have your job is to oversee an automated assembly line that manufactures computer chips. You arrive at work one day to find a stock of 20 chips that were produced during the night. If chips are produced at a constant rate of 5 chips per hour, how large is the stock of chips after working 8 hours of your shift? Okay, good questions all around. So what we can do then is we can first define our variables like we were doing before. So we have, let's use C for the number of chips and T again for the time. And we will say that this time is in hours. So we can set up an equation that will be like this. C equals, we started with 20 chips at the beginning of our shift, and we make 5 chips each hour. So as far as our graph goes, I have to move this over just a little bit. As far as our graph goes, I feel like we should jump by tens here. So let's jump by 10, 20, 30, 40, 50, 60, 70, 80, and 90. So this will be the number of chips, whereas this will be the hours. So what is the question again? How large is the stock of chips after working 8 hours of your shift? Okay, so we know we have to have 8 hours down here. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. All right. So how do we graph this? Well, we always want to put the initial amount right here on the y-axis. We want to find the initial amount on the y-axis. And then for every one we move to the right, we need to increase our number of chips by 5, right? After 1 hour, we would have 5 more chips than we started with, so it would be 25 chips. After 2 hours, we would have 10 more chips than we started with, so we would have 30. And we can continue this all the way over. We can just follow our pattern. There we go. We can just keep going. We can go for as long as the graph exists. And now I'm just going to try to connect these as best I can. Pretend it's a perfect line. So now, using this graph, I'm not even going to use this equation. I'm going to use the graph. How large is the stock of chips after working 8 hours? So if I find 8 hours on my independent axis, the x-axis, and I follow it up, how many chips do we have? Well, if we just follow this back over here, the number of chips at this point is 60 chips. How do we know we're right? Did we graph it right? What's going on? So we can check our work really quickly if we just set C equal to 20 plus 5 times 8 hours. 5 times 8 is 40. We can add 20 to that, and we can see that the number of chips would equal 60, just like we got here on our graph. Moving to the next example, and in fact the final example, we have a country club charging fees, a $30,000 initiation fee, as well as a fixed $5,000 yearly fee. What would the total charges be for 6 years? So for this one, I think it'd be pretty easy to understand that T again is time, And let's say C for total charges. And we'll take our total charges in dollars and our time in years. And you can see that we would use years right here and dollars being here. So let's see here. How do we want to do this? We can set up an equation if we want. 30,000 total dollars to start with plus 5,000 per year. All right, now I have to move this over again a little bit so I can label all of the axes. So here we have charges and here we have time. And we can make the time go all the way over 1, 2, 3, 4, 5, 6, 7, 8, 9. We don't need to stop at 5 even though it's, or 6, even though it's telling us to stop at 6. How can we do this? Maybe we can break a little bit here and start at 30,000. Why would we want to start our graph at 30,000? Because that was our initial fee. And we can jump by 5,000 going up the the dependent axis. So 40,000, 45,000, 50,000, 55,000, 60,000, 65,000, so on. So again, we always want to start graphing from the y-axis, and I'm going to put this number on the y-axis. And as I move over 1 year, I have to add 5,000 to that number. So here we go. I'm just going to keep plotting dots. Ooh, we can go all the way off the graph. All right, now for my, yeah, that was pretty good. All right, now let's see if we can answer this question. At 6 years, how much would you have paid in total? What would the total charges have been? Well, I can follow this up to the graph. There it is. What are the charges associated with 6 years? That is $60,000. Let's see. In total charges. And that concludes the lesson for 9B Part 2. We took a much deeper look into linear functions, how they're graphed, how their equations work, and I hope it was understandable for you. Good luck.